Welcome back, chemistry fans. This is take 2 of Unit 8, Topic 2. We're going to be talking about solubility. So last class, what we did is we learned about molarity and how we can measure the concentration of stuff or solute that is in a solution. Well, now we're going to talk about the extent to which you can put solute into that solution. So there is a maximum amount that can be discovered, and there's also some factors that we need to investigate as to why some materials never can mix together. All right, so we're going to call this solubility, the extent to which the solute can be dissolved into the solvent, creating the solution. So how much solute can dissolve into a solvent? Think about all along while we're doing this, why can oil and water not mix together? So let's jump into this. All right. So one of the key factors that we need to understand about solubility is, generally speaking, once we have an increase in the temperature, we can change how much solute can dissolve for solids. Solids typically increase the amount of their solute, and the gases, however, are the opposite. They actually decrease in the amount that can dissolve into the solvent. And the reason is for the same scenario. In both scenarios, what we have are particles that move further apart. As they move further apart, that allows for more solid to be trapped in between them. But for gases, if you move them apart, that makes a clearer path for them to, because of their lower density, to escape the solvent and become a free gas that is above the surface of the liquid. So one of the other factors, though, is that if we change the pressure or the volume of the container, we can actually hold more of the solutes into solution, and that's true for both of these. All right. Now, why do materials actually stay dissolved? Why do they get dissolved? It's all about this word solvation. Solvation means dissolving. So it is the surrounding of the solute particles by solvent particles. If your solute, which are shown here in blue and in red as positives and negatives in the center, if those particles are completely surrounded by water molecules that are being shown here as these Mickey Mouse blue and reds, then that is dissolved. Once it's dissolved, it is becoming a solution. So you can increase this if we have this idea that positives and negatives, they attract one another and they stay in solution. If we have a scenario where we have negatives and negatives, they will not stay together in solution and they become what is called insoluble. Or we could call this immiscible. Immiscible. So whenever we have these scenarios, we will end up with some precipitants that will fall out. All right, now, some of the important terms that we need to understand, probably self-explanatory for the most, is that some solutions, if we don't have enough of the solute, are called unsaturated. You could still dissolve more of the solute. If it is saturated, it's the perfect amount. No more can be added without their falling out of the solution and being a pile on the bottom of the container. Once that happens, we have reached what is called supersaturation. Supersaturation is too much of the solute and it starts to fall to the bottom as a precipitant. So we call this the precipitate or the precipitant. And in a solution, if you add too much solute, it will eventually fall to the bottom. So we need to understand, how do we know when we've reached that point where we have too much? So we're going to have to understand that, again, solids and liquids, or liquids and liquids that have opposite polarities will like to mix together nicely. But if we have two substances that have the same polarity, they will stay in solution. If they are opposite, they are going to separate. Now, this only happens generally in these liquid to liquid scenarios. That's why these two do not stay together, because of their opposite polarities. But whenever we have solids, they generally break apart to positives and negatives, and we have some pieces for both of them to stay together. All right, now here is how we can decide how much can be dissolved. This is called a solubility curve. So on the left side, you will notice that this is the amount of water. It's 100 grams, which is the same thing as 100 milliliters. 1 gram equals 1 milliliters. So if I have 100 grams, I have 100 milliliters. If I have 1,000 milliliters, I have 1,000 milligrams. If I make that note, I could then say, well, what if I have 200 grams? Well, all of these amounts would be doubled. So let's take some examples. So let's take KCl. It's this line that's right through the middle here. And if I am at 50 degrees, I would be able to dissolve somewhere in the neighborhood of about 42 grams for every 100 milliliters of water. Well, if I have twice as much water, I could actually double that, and I would be able to go up to 84 grams if I double this to 200. But as it stands on this graph, we now see that we have 42 grams as the maximum. Well, what if I added more? Well, if you are above this and you added, say, 55 grams, you are now supersaturated. If you are on the line, you are at saturation. If you are below the line, you are unsaturated. Now, if we want to figure out how much will precipitate if I have a change in temperature, let's take a look at this KCl, and let's say that we are at 40 degrees and we cool it down to 20 degrees. Well, at 40 degrees, we are somewhere in the neighborhood of about 37 grams. At 20 degrees, we are somewhere in the neighborhood of about 32 grams. So if I subtract those two, you would see that I will precipitate 5, because now I still have 37 grams in there, but only 32 of them are able to stay in solution. So we can actually figure out that I would have 5 grams of a precipitant. All right, let's do an example. So if I've got KNO3, which is the green line, and it is at 50, what you would see is that I could dissolve a maximum of 87 grams. If I put any more than that, it will precipitate out. If I have less than that, it will be unsaturated. If I'm right on that line, I am saturated at 87 grams at 50 degrees. All right, the next aspect of this is for us to decide which materials actually will produce precipitants without being supersaturated. There are certain materials that are insoluble in one another, and it has to do, again, with some of their polarities. So this chart breaks it apart into 2 categories. If you're on the top half of this chart, you are soluble. You will dissolve. If you're on the bottom half of this chart, you are insoluble, and you will form a precipitant. Oops, not a precipitant. I think there's an I in there. So now here's what you need to understand. These materials on the left are the ones that are insoluble. They combine with these over here, and there's an exception to the rule. So in other words, if I have magnesium sulfide, notice none of the materials listed over here are magnesium. So therefore, this is not an exception. It will form a precipitant, and it is insoluble. It will not dissolve in water. However, if I have calcium sulfide, it is an exception, and it is soluble. It will not have a precipitant. Let's take a look at the top. If I have bromine combined with potassium, it is not one of the exceptions. So therefore, this will remain soluble. But if I were to use silver bromide, it is one of the exceptions, meaning that it is insoluble. It will form a precipitant. Okay, so let's take some examples here. So I've got all of these are sulfates down at the bottom of the page. Sulfates are always going to be soluble unless we mix with one of these materials. Well, right away, mercury is one of those materials, so it is going to be insoluble. It is going to form a precipitant. Why did I keep writing prep? Precipitant. All right, let's take a look at the next one. Sulfate with barium also is an exception, so it is insoluble and it will form a precipitant. But this third one here is potassium. It is not an exception to the rule, so it will remain soluble. Now, the third one, it is an exception to the rule. It will be insoluble and it will form a precipitant. All right, let's do our final example down here. So let's take a look at all these hydroxides. In these hydroxides, they are always going to be insoluble unless we have group 1 on the periodic calcium, strontium, or barium. It means that this is, well, it's not insoluble. It will dissolve. Zinc is not on it, and it will have a precipitant. Sodium is one of the group 1 elements. It is an exception. Magnesium is not an exception, so this is insoluble and it will form a precipitant. This is everything that I wish to share with you about how solubility works on the periodic table, how it works in reality, and how we can go to. I will talk with you again soon. Bye-bye.